So Roman numeral 4 is going to be on the rotational dynamics section. Do you remember what dynamics means?
It's like study emotion without considering,
With considering, okay. So dynamics was the study of motion with considering the cause. So with rotational dynamics, we're looking at studying things that are spinning with considering the cause. For regular dynamics, the cause was force, and for going to be torque. So letter A is torque. It's a funny Greek letter tau, and the way you can draw it is kind of do this little hook and then curve.
It's like half a pie.
Yes. Without the, yeah, that makes sense. If that's kind of difficult, you can do like a little loop with a T and do that instead. Either one's fine, whatever's easier for you to draw. So torque, curvy T. And a torque means a twisting force. So instead of pushing or pulling, you're actually going to twist and cause something to rotate or spin. And it can be found by multiplying force and lever arm. These two boxes, pick whichever one you like better, they mean the same thing. So force is in both of them, and then for our lever arm, I put perpendicular L, because for you guys, your lever arm's always going to be perpendicular to the force. If you read your book, it'll say times sine theta. I'm always going to give you 90 degrees, so you don't have to worry about the theta part.
So it's just going to be force times 90 degrees?
It's going to be force times the lever arm times the sine of 90, and sine of 90 is 1, so we're just dropping that part off.
Would you say it's going to be perpendicular to what?
The force and the lever arm are perpendicular to each other. If it's easier for you to remember, a lever arm is very similar to a radius, so you could just say torque is force times radius. So if that makes more sense, go with that version. And then on the slide, it's got a couple of demonstrations. So we're going to use the door to show you where a lever arm is. So I'm going to push, and that's going to be my force, and then where I push is going to be the lever arm. So the door swings like this. This is our axis of rotation. If I apply a force way out here, that distance from the hinges all the way out, that's your lever arm. Okay. And then when I apply a force at that distance, I've created a torque, so now the door will swing and spin outwards. Okay. Do you think it's going to be easier or harder if I do it here? Harder. It takes a lot more effort. So when it asks you questions about torque, it depends on two things. It's one, how much force you apply, so how hard you have to push, and where you push. So that distance is important. And after your notes today, you're going to get a chance to do several little mini labs. There are 10 available. There's actually 9 available because I'm missing stuff for one. You need to do 5 of the 10. One of your options is to use this thing, and this is the little torque feeler. So the force is going to be the weight that hangs from it, and then the lever arm would be the distance out to where it's hanging. So in this case, from the handlebar out midway, if that's where I hang the weight, that's a lever arm, versus all the way out, that's a larger lever arm. And then what you'll do in your lab is pick those up. I can't do the one at the end, but you'll pick it up and you want to try to keep the T-bar level with the ground. Okay, so Dana should be able to do this one all the way out.
Is it so heavy?
Yeah, it's like really hard. It kind of twists, and then once you let it go, if you lose your grip, it's going to drop and spin like that. So that's where the rotation part comes in.
I thought it was supposed to be easier than if it's like
On this one, it's because gravity is working against you. So the further out it is, there's a larger torque. So it's going to be more difficult in that case. And
So
Dana, if you want your options.
for the labs count that we did last class, is that towards your 5? Or
Yes, that is towards your 5. So if you were able to finish 1 or 2, that counts towards your 5.
okay. They're almost the same.
So last time when we studied dynamics in chapters 4 and 5, we talked about Newton's 3 laws. We're going to take those first 2 laws and apply them to things that spin instead of move in a straight line. So if you need a reminder, if you have the printed copy of the notes, I've got the law filled in for you. It was if there was no net force, then there was no acceleration. That was your law of inertia. So if something was moving forward, it was going to continue to move forward until you stopped it. For rotary motion, we're just going to replace force with torque, and then we're going to replace acceleration with angular acceleration. The concept is still the same. Okay. Before, if you don't apply a force, something's not going to accelerate. Okay. If it's moving, it's going to stay moving. Here, in order to make something move, you have to apply a torque, which is a twisting force. So all we've done is switch out our letters, force for torque, and acceleration for angular acceleration. And on the bicycle wheel, when we studied Newton's first law before and we just simply move it like side to side, then it's accelerating. But if I just hit it with a force and try to move it, it's not spinning at all. I have to twist a force to make it accelerate. So there's a difference between accelerating side to side and accelerating the way it spins. For this chapter, we're interested in the spinning part. So if I hold it still and I just apply a force, is it going to spin? Nope, it just stays there. You're just hitting the wheel, it's not doing anything. You have to apply a twisting force to make it spin. And that twisting force is your torque. So on the first law, if there's no twisting force, it won't accelerate, it won't spin. That's all that's saying. Okay? So if you don't twist it, it's not going to spin. Do you have questions so far? Okay. I'm going to leave these out too, so you can play with them this week and then next week as well. So for our second law, I kind of covered up some things because I didn't want you to get too far ahead. The second law was the formula one where you have F equals ma. When we're talking about things that are rotating or spinning, we're going to take the word mass and replace it with this thing called moment of inertia. And moment of inertia is something that depends on the amount and the distribution of the mass. So for example, have you ever seen the ice skater when they're spinning around in a circle and then all of a sudden they pull their arms in, they spin really, really, really fast? Does their amount of mass in their body change? No. Okay, so it's still the same person. They have the same amount of mass, but what's changing is how they're distributing that mass. So for moment of inertia, if something's really, really spread out, it's got a big moment of inertia because the person, like this would be your axis, you have a large radius. You have things very, very spread out. That's a big moment of inertia. If you tuck in tightly, that's going to be a small moment of inertia. It's not spread out at all. And then what we're going to do is take our new letters and rewrite Newton's second law. So force is now going to become torque. Mass is now going to become moment of inertia. So it will depend on the mass, but also how that mass is spread out. And then acceleration is going to be angular or spinning acceleration. And then over to the side, I wrote out what each of those are. If that helps you, you can define the variables off to the side. Another of your labs is going to be these meter sticks. And I'll give you a chance to write, and then I'll show you what you're doing with each of these.
$30.
Yeah, thanks. And you might want to make sure that these are taped on kind of tight, because last period I was like, woo, and it flew off and hit the window. So, okay. So make sure the quarters are taped on. So what we're doing on this one, you have your moment of inertia, and you're going to twist it so you're applying a torque, and you're interested in how fast you can make it accelerate. So how fast can it spin around? And if you hold it in the middle and they're really, really close, is that going to be easy or hard? Easy. So it's like really easy to spin that back and forth. The reason for that is that our moment of inertia, the I, it's really small because more of the mass is toward the center. Okay, it's more compact in the middle. So that's a small moment of inertia, which is a big acceleration. They're opposites. It's kind of like when we did the second law before and we talked about like the big 18-wheeler has a really big mass and it's hard for it to accelerate. Same kind of thing. On this stick, the masses are spread out at the end. So when you try to accelerate it, it doesn't spin as easily. You have a large moment of inertia because it's really, really spread out. So a big moment of inertia, small spinning acceleration. They are opposites to each other. Kind of makes sense? So the torque will stay the same. The I and the alpha, those two are opposites. They constantly exchange to balance each other out to keep the same torque. Okay. Do you have questions? On your copy of the notion that asks you about a disc and a hoop and which one spins easier and why. So we're going to have a race. I didn't have a disc and a hoop, but I have something really similar. Both of these black discs have little metal balls inside of them. One of them has the balls in compartments in the very center, and the other one, the balls are spread out in compartments on the outer edge. Okay. If I were to race these, which one do you think is going to spin easier and when? So we're going to race them, and then we'll pick it up and see which one. Okay, so I'm going to let go. Thank you. So this one won, so we're going to open it up and see.
Suspense.
So this one spins easier. Wow. So they were in the middle. Okay. So that's the same as the meter stick. When the masses are more concentrated in the center, it's going to spin more easily.
Is that a disc?
Thanks. So that would be the disc. So the disc represents the mass being more concentrated in the middle because it's solid inside of it. And it has a small moment of inertia because more of the mass is in the center. There's a very, very small radius. It's all concentrated in the middle. So it's going to spin easier. The hoop, it would be a hollow circle. Okay, there's nothing in the middle. All the mass is on the outside of it. So on ours, we just place the balls on the outside. And so it has a bigger radius because the mass is further away from the middle. That's going to be a big moment of inertia and a small angular acceleration. It's really difficult to get up that speed to make it start rolling. Questions? Now we're going to look at angular momentum.
Is this the last thing we're doing?
This last page. We've got a few examples for it, but it's the last of the concepts. So the homework you turned in today, most of it was on regular momentum. That was for something moving in a straight line. This is angular momentum. If you printed the notes, it's a capital L for the symbol, and it gets conserved just like regular momentum.
Oh, sorry.
What was the formula for regular momentum, the linear one? Yeah. Okay. So P equals mv. So if P equals mv, now we're going to take those same things and replace them for things that are spinning. Okay. So the P is now an L, and that's angular momentum. So instead of just saying plain momentum, it's angular momentum. Do you remember what mass gets replaced with? I, which is moment of inertia. And then our V will be the omega, like in your focus activity question, and it's spinning or angular velocity. That word angular, it can mean anything that's spinning or rotating. So those are all interchangeable words.
Is that a T?
That is an I. It's an L, an I, and an omega. So the L is the angular momentum. Okay. It's very similar to inertia. It's going to refer to motion that's spinning. The I is moment of inertia, which is how spread out you are and how heavy you are. And then the spinning velocity is how fast can you rotate. Questions? We're going to do a bicycle wheel example.